product offering. Dr. Pratibha Anantanamu drives innovation in receiver analysis, signal simulation, location and navigation, and receiver validation methodologies is the areas she has actively researched since 2005. I welcome you, ma'am. So I welcome both Bharathidhasan sir and Dr. Pratibha madam for sharing this session. We are eagerly awaiting for gaining many practical exposures from you both. Thank you, sir.
Yes, ma'am. Thank you. Thank you so much for the introduction. Can we proceed?
Yes, sir. Please, sir. Good evening, sir. Please proceed, sir.
Good evening, all. Okay, before we get into the subject, I would like to give you a brief introduction about Accord. I mean, we are working for Accord Software and Systems. I would like to briefly give you the background of Accord. And I always feel, it is not like normally people do, what they do or how they do. Very important is why they do. Just want to tell you the background why we got into simulator. Just only these two things before I hand over into Dr. Pratibha. See, Accord Software and Systems, we have been working on GNSS technology, basically the GNSS receivers, GPS, GLONASS, Beidou receivers, and its related products for more than 2 decades. And today, Accord's products are being used in land, for example, most of the defense application, naval application, and airborne platform, including satellite and launch vehicles. Okay, it's being used. The second part is simulator. We never, worked on simulator until to get a project from ISRO. This is a very interesting. Like Accord was working all these years for GNSS receivers when the NavIC, you might be aware, this IRNSS was planned by ISRO almost 10 years ago. So before they started launching the satellites, they had to install a ground station in Bangalore. For that, we also participated in the tender. Accord is one of the tender participant for making the receiver for the ground station. When the satellite itself was not there in the space, NavIC satellites was not there at all. So to test the receiver, we have to use simulator. So to complete that, project, which is part of the tender, we had got a quotation from one of the company. I don't want to name the company. It is like the receiver product is ours. The receiver was planned to be tested by using a simulator which is from abroad. Okay, Accord participated and the same company also participated. Fortunately, we were L1. I mean, we got the project, technically qualified and commercially lowest. We got the project, but then when we approached the company who had quoted the simulator, when we approached them later after getting the project, they refused to give us. Okay, because if we are not able to execute the project will be given to them by ISRO. So we were thinking internally, what do we do? How do we do? And it's a great challenge for Accord. Then our program director, Dr. Vyas, decided that let us develop ourselves. Only simulator we have left. We have already developed all other things related to GNSS technology. Thinking the team strength and expertise, he took a challenge that, okay, let us develop within Accord. So that is how we started our simulator career, journey. We developed our first simulator for ISRO project, then followed by, now there are so many simulators, and simulators, based on simulators, we have made so many products which we are delivering it to Army, Navy, Air Force, and even paramilitary forces, which is doing very good. and Dr. Pratibha is one of the lead in the program. And I now hand over it to Dr. Pratibha to explain further about the GNSS simulator. Over to you, Pratibha.
Thank you, Bharti. Thank you for giving the brief introduction. Mukesh sir, am I audible?
Yes, madam. Yes, madam. Good evening, madam.
Okay. Yeah, good evening, sir. First of all, I would like to thank Padma ma'am for the warm welcome and introduction, and Mukesh sir for giving me an opportunity here for presenting GNSS related topic. I would like to share my screen. Sir, is the screen visible to all?
Yes, madam. It's visible.
Okay. So please let me know if the screen's stuck somewhere or you're not able to view, because I'll not be knowing.
Yes, madam.
So, yeah. Hearty welcome to all the participants of this particular training. So, I'm pretty sure most of you are well versed with the GNSS concepts and its applications, the receivers and its mode of technology that is booming in the market as on today. So I would like to take all of you into a topic called GNSS simulator and the applications of the simulator, or why do we need this simulator? How does the simulator help the academy or the students or the researchers who are trying to build something new in the GNSS domain, particularly in terms of the NavIC related receivers? What best can be done? What are the research opportunities? How simulators, or what kind of simulators are you looking for in the market? How do you choose a simulator? So I'll try to dwell in these concepts so that all of you can be slightly aware by the end of this session on the simulator and its applications towards the GNSS domain. So the main agenda for this presentation is I'll be giving a slight introduction into the GNSS basics and what are the need, as I told you, on the GNSS simulators, and what are the required simulator features, or there are lots of simulators in market. What features are required for what kinds of receivers? I'll be dwelling into that. And in the end, I'll just give you a market survey of the simulators, where it stands today. Building of simulator itself is a challenge for many people, as Bharti has already put it out. Like we did simulator for need of what it is, saving our cost to the company in terms of the project outflow for the IRNSS receiver program. So this has helped us in a lot of way, and we have learnt a lot in the GNSS simulator domain. And I would like to put across to all of you what are the things that will help you moving forward in your research or the areas of development that most of you would like to follow in the due course. Please, you can raise hands if you have any questions in between, or you can just leave a chat here so that I can answer them. Okay. I'll be sharing the screen, so I might not be able to see your chats, but I'll try to see in between how I can take you to the presentation. Okay. Sorry, I was just running across the simulator slides. Okay. Okay, I'll not take too much of technical equations in my presentation. I will try to keep it as simple as possible so that it will be easy for all of you to understand, and it will help you gain sufficient knowledge on what we are planning to do. So first and foremost, let us talk about the basics of navigation. So what do we actually mean by navigation? So basically, we as a GNSS engineers, we always see it as an art uh, of the science faction, where we are required to answer two basic questions. Basically, where am I and how do I get to my destination? This is the only thought process of any GNSS engineer. how to get to my destination, how quickly, how in a very shorter distance, how efficiently, how using minimal resources. So a GNSS engineer always tries to identify where he or she is in any particular location and how to get to another destination. So basically, these two are the only things that bothers us. Now, if we go to the history, how did people really navigate? So the old man, he used to navigate using landmarks, stones. They used to carve on trees, or they used to make marks using stones throughout their way. Next was an advanced feature where they moved into celestial objects using those stars, moons, traces. They used to navigate whenever it was feasible. Mostly it was in the night because it was very beneficial. Further came a sensor-based navigation, wherein they used compass, the barometers, magnetometers, different kinds of sensors, which helped them to an additional benefit. Further came the enhanced radio systems. So these radio systems help to talk to each other in two different locations, trying to communicate with each other, trying to help them navigate right, left, front, based on whatever is the feasible technologies. Finally, with all the advantages, pros, cons, we have our satellite-based navigation systems, which is predominantly the GNSS-based technology, which is helping us to navigate throughout the world using the help of the satellite signals. So we will dwell into these signals. How do we use these signals in the upcoming slides? So what is GNSS? So because most of you are already experts in this domain, I will not dwell too much into details of this. However, let us just get into the basics. So GNSS is a global navigation satellite system. So it's the acronym for Global Navigation Satellite System. So basically, this is a navigation system which is capable of providing you data for the computation of your position, timing, location, anywhere, anytime, under any weather conditions. So you don't have any baggage that this system will not work in this particular condition. So the assumptions are very minimal in terms of satellite-based navigation. And it also adapts advanced CDMA or FDMA, that is code-based multiplexing or frequency division multiplexing technologies. So inherently, this has an feature of providing immunity to unintentional jamming or interferences. So this was an added advantage in terms of the GNSS systems. And one main thing of the GNSS was it was a standalone navigation system. It did not require any aiding whatsoever to give you the basic capability of a navigation. And in terms of the cost, it was very low cost compared to all the existing technologies like the VOR or the ILS systems. So this definitely helped the users to get attracted to the satellite-based navigation systems. Now, if you look at the pioneers of the GNSS, so we have the GPS, which is from the US, the Global Positioning System, and next came the GLONASS, that is from the Russian systems, followed by IRNSS, that is from India, and Galileo from European Union. Baidu came late, but they are already progressed in the market more than most of them. They have more number of satellites compared to any one of the other constellations. And we also have quasi-zenith satellite system from Japan. So if you see, each and every system have, uh, anyone has any questions? Sorry.
Nothing, madam. Please, madam.
Okay, so I'll continue. Okay, so these were the main GNSS satellite systems of each of the the countries that owned them. And they also felt the need for augmentation satellite systems. So if you can see, there are lots of star marks on the screen. There is something called WAS, Wide Area Augmentation System, to aid the GPS satellite signals. IGNOS, this is for the Galileo signals. SDCM was a satellite system augmenting the GLONASS. Similarly, for IRNSS systems also, we have something called GAGAN. So even the Japan systems have MSAS. They also provide for GPS. So this is a total overview of all the GNSS systems that is currently available in the market. Sorry, in the space, not in the market. So just a brief history, whatever I explained now. So GPS was launched in 1980. GLONASS in 1995. Both India and European Union, they started their own navigation systems in 1999. In Jan 2006, China came up with its own constellation system called Compass, currently being called as Baidu throughout. And Japan has its own constellation in 2010. And most of the constellations that I have defined here, they are in their full operational capability, except for IRNSS and QZSS, which is a regional capability system. Rest all are global capable systems. So if you have any receivers which are capable of any of these constellations, you will be getting position throughout. Now, dwelling into the different segments of GNSS, like for the satellite system to work or the navigation technology to work, there are several segments that play a major role. So, in terms of the GNSS, there are three segments. One is the control segment, the second is the space segment, third is the user segment. So, the control segment basically consists of multiple monitoring stations, master stations, or the ground antennas, which basically do the controlling of the space segment. Space segments are generally the satellite constellations which beam the satellite data, which is used by the user segment. So user segment hosts all the GNSS receivers that are available in market, which are making use of these GNSS signals. Now the master stations, what do they do? So the control segments, which is comprising of master, monitor, and ground antennas, they basically control the measurements of the satellite signals. Towards this, there are multiple monitoring stations placed across the world. If it is a global system, like if it is a regional system, across the region, you'll have multiple monitoring stations. They'll day and night monitor the satellite systems. And you also have ground antennas, which will uplink the updated navigation data to the satellite signals. So basically, this is the main heart of the GNSS system. Next comes the space segment. So when we talk about the space segments, basically it consists of the satellite vehicles or what you call as the space vehicles. Most of you would have seen in any GPS app, SVID1, SVID2. SV is nothing but your space vehicle. So, and there are different orbits that are preferred in GNSS. So main three orbits that are considered in the GNSS satellite signals are the geostationary. Most of the augmentation satellites, they are on geostationary. And geosynchronous, mostly it is Baidu and IRNSS, which are on the geosynchronous satellite orbit. And most of the remaining others, GPS, GLONASS, Galileo, they all are on the medium Earth orbit satellites. So their orbit is such that every 8 hours you'll have a new constellation across the same location. So whenever you're tracking any satellites or you're doing a receiver analysis, you can see that the constellations are changing. That is because of the characteristics of these satellite orbits. So if you can see, this is how the satellite orbits are placed. Like if you see the GPS, you have 24 satellites, 4 in each orbital planes. We have 6 such planes, so which will give you a full constellation capability anytime, anywhere on the Earth. Now, if you see the Galileo, they have only 3 orbital planes. However, they have 27 satellites, so 7 in each of the planes. Now, if I come to GLONASS, GLONASS has 3 orbital planes similar to Galileo, but they have 21 satellites. The number of satellites in GLONASS is less compared to the other constellations. And lastly, what we see here is the Baidu. So if you see here, they have 6 orbital planes in GEO as well as GSOs and MEO. 30 satellites is what they claim, but if you switch on any receiver which has a Baidu capable, you can see more than 30 satellites. They are just pumping up the number of constellations in the space. Now, if we talk about the user segment is any receiver which is used in anywhere, in any transport systems or in any application, space, air, water, you name the place, you can find your user segments. Your phones, for example, your car navigation systems, or the truck offloading systems, or the ship docking systems, or the aircraft systems. You name the systems, everything has GPS in it. Which wherever you use navigation, now it has become a part and parcel of each and every navigation system. Without GPS, life is becoming very difficult. With GPS, also life is becoming difficult because people are finding ways to tweak GPS, which is providing ample of opportunities for all of you researchers to come up with novel, innovative technologies. to counter all the insignificant or the what do we call unintentional or intentional interferences that are haunting the GNSS signals. Now coming to our own IRNSS, we call it as India's own GPS. So this is Indian Regional Navigation Satellite Systems. So it was a wonderful program that was indigenously developed by ISRO India. Basically, it provides Indian military an independent navigation system. And why do we need an independent when we have so many constellations and everything is free? If you see every other GNSS, they have open service signals. That means you need not pay them. So if your receiver or if your equipment is capable of receiving those signals, then you're good to go. No one is asking you to pay, no one is questioning you. So why do we need an independent navigation system? Basically during hostile situations. This is very much important from a military perspective. Just few months ago, we had Operation Sindhu. Most of our assets, they are equipped with GPS and GLONASS. For whatsoever reason, if US takes a call, I will switch off GPS over Indian subcontinent, which is feasible. Now, none of our assets might work at that point of time. So IRNS becomes a mandate for us because no one can switch off IRNSs, and IRNSs will provide us a seamless navigation. So we should always have our own navigation system. So we should thank ISRO for coming up with this particular system, deploying it, maintaining it, and ensuring we are independent in terms of navigating ourselves. And with respect to the IRNSs, similar to other technologies, it also provides the standard positioning services signals for the civilian use and also restricted service for authorized users. So when we tell restricted service, this is exclusively only for Indian military, wherein only the MOD authorized receivers or MOD authorized programs can only use the restricted service signal, which can be used in terms of in hostile situations where we can still switch off the SPS, but we can continue to use our military assets with the RS signals. So this is a wonderful benefit for our Indian military, exclusively, if we have to put it. And the goal is also very simple. All three segments to be built in India, Atmanirbhar Bharat, Made in India, Make in India. In terms of all the three segments, I think they have achieved most of them in India, and everything is in place today. And if you see its capability, it provides accurate real-time positioning and timing services over India, extending 1,500 kilometers around India. So it's a very large footprint, which is sufficiently capable for our tri-services in terms of Army, Navy, Air Force, BSF, for it to provide independent navigation on sea or on ground or in the borders. So IRNSS has become a pioneer now for all the markets in terms of its capability and in terms of its convenient in terms of having our own navigation system. So the operation name is NavIC, which we call it as navigation with Indian constellation. So IRNSS and NavIC, most of the times we interchange it, but NavIC is a very nice name, which we try to use it most of the time. Now, this is a pic from our ISRO website, so which depicts the IRNSS architecture. Similar to any other constellation, even the IRNSS also falls under the same category of control segment, the space segment and the user segment. So we can see that in detail, we have lots of control stations here. So each and every control station has its own capability and its own functionality. So if you can see here, we have the uplinking stations, the spacecraft control centers, and lots of timing centers, the CDMA ranging centers, or the IRIMS, the laser ranging centers. So all these centers, they are 24/7, 365 days of the year monitoring the satellite signals and trying to check if there is any issue with the satellites, trying to upload new satellite information so that the users can have continued navigation. I'm sorry. So the control segments are very effective, and they are on their toes 24/7. Whatever Bharti was explaining, we had provided our receiver to one of these control stations, which would also help them in monitoring the satellite transmitted data. So that was the place where we didn't have a NavIC simulator, and we were forced to develop a NavIC simulator. but that turned out to be a blessings in disguise for us. Sorry, as a company. Sorry. And if you see, ISRO is structured as 7 satellite configuration, 4 in geosynchronous orbit, 3 in geo orbits. However, recently 1 or 2 satellites they are down, but ISRO is making all efforts to ensure everything is up and running with the latest state-of-the-art signals, which have been newly defined by the ISRO committee. Now, as I mentioned, this is the satellite configuration. Sorry, and the coverage that is being shown, wherein the entire user segment which lies in this particular segment sorry, I have little bit cough and cold, so I might stop in between. So this is the constellation footprint which we can ensure that all the user segments across the Indian subcontinent are capable of providing uninterrupted navigation solution. Now, the applications of GNSS or IRNSS is huge, vast, and unimaginable. So I have just given a brief summary of the applications. So if you can see, you name the application, you can use the GNSS receiver or its beneficial features here. So in terms of the surveying, when you want to have an accurate mapping of the survey location, or in power grid interfaces where you want to have an accurate timing for the power grid monitoring, or in terms of agriculture where you want to do an sowing of the seeds in a defined manner, defined path, wherein GNSS aids you in giving that particular path. Trucking, shipping, most of the truck companies are benefited with respect to the truck mapping or the truck tracking, wherein they have become more and more efficient in terms of shipping of the items and in terms of customer satisfaction. Aviation industry is one of the largest industry which has benefited from GNSS, wherein they have minimized the maintenance efforts on the other non-GNSS navigation technologies which were used in the past, and a GNSS which is very, very low cost in terms of maintenance. And several other environmental management or the construction, civil engineering, the offshore drilling, you name the applications, you have those applications which can be mapped to GNSS. So even any field that you take, GNSS is being very, very helpful. So to summarize the application areas, so as I told you, terrestrial, aerial, marine navigation, which is one of the major stakeholders of our GNSS receivers and its byproducts. Disaster management, basically, if you want to pinpoint a location of fire or you want to pinpoint a location of any fire in any of the floors of a big building, so GNSS is definitely helpful. Your vehicle tracking, fleet management, the mobile phones integration. Now it's like just click of a button. You will be able to get your location. You'll be able to get the fastest route on your phone. All this is feasible because of the GNSS technology. And one of the biggest byproduct of a GNSS technology is its precise timing. The timing is because of the atomic clocks that are used on board the GNSS satellites, which provides us accurate data, and any receiver which is efficient enough in its implementation can give you timing as accurate as in few nanoseconds. So this is a huge, huge benefit of the GNSS, which was initially not intended for, but this has become a very big booming market for the GNSS receivers. And the other 3 are for the personal or the recreational activities, the terrain navigation for hikers and travelers so that they don't lose their way. Mapping and GIS, that's one of the biggest domain which has made most of the use of GNSS, where maps are getting updated using precise GNSS receiver data. And visual and voice navigation, most of you are aware, you use it in your phones. So you can keep naming the applications, it is endless. Now, when we talk about the GNSS receivers, so all of you might be thinking, how do you know whether this receiver is good or not? Or what do you want to see in a receiver? Like generally, when you buy a mobile phone, you will have certain features. What is the RAM? What is the memory? What is the speed? Or what is the screen size? So there are lots of metrics for a phone or for a laptop or anything that you buy. Similarly, even when you're either building a similar receiver or whether you're procuring a receiver, you should know what are you looking for in the receiver. I have listed here top 10 performance metrics, which will help or guide you even in your innovation. Like you are building a new technology. For what are you building a new technology? So I have listed 10 main points which will attract your customers, which will attract your investors, or which will attract your research. So, anyone has any questions? Sorry.
Nothing, madam. Some interruption, madam. Please, madam.
Okay. Okay. No issue. Okay. So, the first and foremost is time to first fix. So, whenever you switch on your phone, the moment you switch on Google, your location is displayed there. So how quickly can you give your position? This is one of the most important factor. If you give your position after 2 minutes, no one will like it. Now it is 2 seconds. So we call it a snap start. We have hot start, we have warm start, we have cold starts. There are different kinds of starts, but everyone wants a snap start. Just snap of your finger, you need the position. So how quickly can you give position? It's not easy to give position very quickly. There are lots of technologies or lots of algorithms that goes into it. So that is one of the measurement. Next is the reacquisition time. So how quickly after you lose a signal can you reacquire the signal? So if we are using it for personal navigation, you might go under bridges, or you might go over passes, underpasses, or you might go in an urban canyon where the signals are blocked. So how quickly can you give me back the position? So that is also one of the criteria. Third is sensitivity. How sensitive is your receiver? How low can it look for a signal? Or how high an interference will not affect your signal or your receiver performance? Now, fourth is a feature that everyone mandatorily wants. Basically, how accurate is your position? So, in static, at least you can do a Kalman filtering if you know it's a static signal, and you can continue to give your position. But in dynamics, it's not like that. You cannot use a Kalman filtering over a longer duration for a dynamic scenario, which is varying continuously. So, how good is your receiver in providing you the required accuracy in dynamics as well? Now, fifth is the long-term stability. So, if you know there is an atomic board on board the satellites, there is also a clock on your receiver as well. How good is your clock? How good can you tune the clocks? How good can you give long-term stability in terms of your timing measurements? That is also a parameter of your receiver performance. The sixth is the influence of the external parameters. So how good is your receiver immune to external interferences? It might be intentional interferences like jamming, spoofing, or unintentional interferences from any other RF signals, or multipath, which is a major factor that a receiver might not perform good, or also the atmospheric models. Basically, all the signals, GNSS signals, they pass through our atmosphere, which is comprised of tropo and iono, which definitely affect the signal type. Now, the seventh is the leap second insertion. So all of you are aware that we keep correcting the leap second when our reference clocks drift by a second, right? Now, is your receiver capable of that? Otherwise, if you are using that receiver for timing, then there is no use of that receiver. So how good is it in terms of the leap second corrections or the insertions? The eighth point is the timing receiver. How good is your 1 PPS signal? What is the accuracy? What is the reliability of that 1 PPS signal? Nanoseconds, microsecond, millisecond, does it drift? Is there an offset? So this is also a receiver performance metric. Ninth is the ionospheric modeling. This becomes very, very much important when you are installing your receivers across the equator where the INO activity is very high or comparatively high with respect to the other quadrants of your Earth. So, ionospheric modeling, how good can you do, and how best your receiver can incorporate those modelings and do an nowadays it's all AI based modelings. Now, can an AI based modeling be included for ionospheric, which is ever varying? That's a topic of research for whoever is interested. So, if you see most of our augmentation satellites, they give ionospheric corrections. They give corrections to the ionospheric data because they are monitoring the local ionospheric errors. So all the S-bars, Gagan, they all give you add-on errors, the clock errors, INO errors, so that we can improve the signal accuracy. And last part is, yes, I told in the first statement that GNSS is self-sufficient. But if you add GNSS, how can you improve the performance? So if you see GNSS is a long-term stable, INS is a short-term stable. How can we combine them so that we can get benefits of both long and short-time measurements? And how can we improve the system performance? Everything that we are talking is to ensure how can we improve, how can we progress, how can we benefit. So all these features, when we take into consideration, brings out the best receiver that is useful for the market. Now, because all of you are from the research background, I thought to put 3 slides on the research opportunities that you might be interested in. So basically areas in the receiver design, as I mentioned, a software defined radio, which is tunable based on the external scenarios, the algorithms that are required for the different kinds of positioning for high precision applications, guidance, marine, airborne, different kinds of weather applications wherein receivers design can be adopted to, and GNSS exclusively for challenging environments where the performance of GNSS, all of us know, is very poor in indoors or urban canyons. Nowadays, if you see any ion paper or GPS World or GNSS market research, there are lots of major magazines. They are giving you day and night lots of algorithms. How can we use those algorithms for our applications? Or is there anything better that we can do for the existing technologies? So there are lots of research opportunities in the design. And the latest in the market that I think most of you are aware is, how do we make our GNSS receivers immune to interference? It can be any kind of interference, jamming, spoofing. So you would have seen the latest boom is CRPA antennas, anti-jamming antennas, anti-spoofing receivers. So these are the markets which are growing now. And on the other hand, there is also GNSS, which you would like to put it on a drone, because drones are a booming market now. And for an coordinated systems, timing solutions. So these three are booming like anything in terms of the GNSS receiver market. And for somebody who is exclusively into error modelings, so the GNSS offers research opportunities in multiple domains. It might be the modeling in terms of for the satellite based errors, which is the orbit or the clock errors or group delay because of the multiple configurations of the satellites, or in terms of the propagation errors where we have different kinds of error introduced onto the GNSS signals in the form of inotropo errors or the multipath or interference errors, or your own receiver technologies wherein the errors can be because of the different kinds of antennas that you use, or the receiver clocks, or the noise characteristics of the receivers, the different kinds of receiver based errors. And the third most, which is very much useful, is, as I told you, how do you aid GNSS with other systems so that we can improve the system integrity, system reliability, or the system performance. So a lot of aiding like S-bars, as I have already mentioned. G-bars and DGNSS is something which is exclusively used during our aircraft landing scenarios, or the INS, wherein most of our missiles, they have a GNSS INS fusion solution. And just to give you all an insight, like Accord has delivered missile specific GNSS receivers, which has gone into most of our indigenous missiles, Astra or BrahMos. So we have been providing GPS GLONASS receivers for our missile applications as well, wherein it is integrated with INS to get a better performance characteristic. So how do we improve this? How do we bring out new research in this for the benefit of the market? And there are lots of others wherein you can define something called GNSS pseudolights for wireless location in GNSS denied environments, or integration with Bluetooth, Wi-Fi for all the mobile applications. And recently, the IOTA thing, the Internet of Things. So you have lots of opportunity where you can just integrate GNSS positioning with anything in your home and try to get your own custom IoT devices. Now that we have talked a lot on GNSS receivers, now you have a receiver. How do you validate the receiver? So there are lots of validation technologies. Because you have live satellites available, we need not bother. That would not be a right statement, because live antenna provides you only limited test cases. And I'll talk about it in detail later. And we also have a concept of field test, wherein we drive for your dynamic analysis. We place our antennas on vehicles and move around different places. Now, if you're building a receiver for high dynamics applications, you cannot do a flight trial or a field trial because it is heavily costly. And seeing all these backgrounds, what we see is simulation is one of the best cost-effective solution, repeatable. You can repeat the experiments n number of times without having a question mark on the input data. And there are lots of advantages. So these are the different which will still hold good even today. Your first test will happen with live antenna. The second test will happen with field test. The final clearance happens with the actual user application domain. However, for all the above three to pass, simulation is a must for any of your research applications. This is something that is really required. And this is, I just brought up an image here. He is Chris Hadfield. He is happily singing in the space station. Do you think he would have been able to sing there if he had not been trained in the simulation that happens here on ground? So the importance of simulation, I just wanted to highlight here that how good the simulation will help for a smooth execution in the real time. So this is really required. So this is a human in-loop simulation of the outer space, which happens on ground, where they simulate exactly the outer space environment and allow the astronauts to be in that scenario, try to experience that scenario, so that when they're actually in the scenario, they're already accustomed to it. Simulators or simulation provides us exactly the same thing. Any simulation and training platform, they provide us innovative approaches to validate our system and to know the effectiveness so that we can achieve more with less efforts. So this is how I always think a simulation is. Now, just to give you a brief, what do you tell, summary of why should we go to a simulator. So I have just listed only few of the advantages. So if you see the cycle of simulation usage, so we do some design, you go through a simulation. Now you analyze the results after simulating. Now, if your validation gives you a go ahead, then you're good to go. Otherwise, you always have an opportunity to improve your design. So you need not go to the market until and unless your system is proven here. And if you see here, the benefits of your simulation is it is cost and time saving, because you are not actually doing your field trials, which is very costly. It is also saving your time because you're repeatedly doing the simulations here. It is quick. And you're also able to optimize the product performance. So the product performance optimization is in the benefit of everyone, because when it goes to a manufacturing or a production house, if your product is not optimized, it's of no use getting that product into production. So before we actually release any product to production, it has to be proven. So to prove it, simulator gives you n number of flexible test cases which can be repeated for its performance validation. So what does it generally give you? It gives you complete control of your inputs and outputs. outputs. And how do we validate? It gives you flexibility to change your inputs and try to see how your system is behaving for the changes in the input. Is it a bounded input, bounded outputs in a design, or even for your bounded input, your output is going unbounded. So you can validate where all your design is going wrong by doing the lot of by providing different kinds of inputs to your simulation platforms. And third point is completeness. We can do complete testing using a simulator setup. I can tell this with complete full guarantee because we have developed a missile receiver using a simulator, and it has been successful and is successfully flying. Most of our Cartosat satellites have our GPS GLONASS receivers. So the simulator, when built properly, when having the proper features, will give you complete platform testing and validation. Of course, there are lots of platform related unknowns which we can definitely get in the simulation in the actual runs, but that will be very minimal compared to how we do the complete simulation. And one of the factor is your simulations can be repeatable. You can do the same simulation again and again and again and try to check which design is best. Next, reliable. Because you know what you're simulating, you know what you're expecting, it's a reliable source of your design aspect. As I mentioned, cost, efficiency, and it is almost realistic in nature, mimicking the live scenario or the real time scenarios. And with respect to our own experience, we were able to validate future signals which were not even there in space in terms of NavIC. We were able to simulate it and we were able to validate our receiver. Also, in terms of Galileo or GPS or GLONASS, all of them are coming up with new constellation signals. The signals that are there are 10, 15 years old. Now they have come up with new navigation signals like all the L1Cs, like GPS L1C, GLONASS CDMA, IRSS L1C, Baidu B1C. All these are upgraded satellite signals. Now, I don't have satellite signals in space, but if you have a simulator which is capable of simulating this, you are future ready. So, with respect to the simulator, we can keep on listing like the applications of GNSS, advantages of simulator, we can keep listing and it is endless. Now, what does an actual GNSS simulator do? So what does a simulator do is it will try to generate the signal as though it is being received by the actual antenna. So it will simulate the GNSS satellite orbits, it will simulate its path, it will simulate the inotropo errors, it will simulate the antenna characteristics so that a GNSS receiver will feel as though it is seeing signal from the live. So this is a generic GNSS simulator. Hello? Hello?
Nothing but a small interruption, please, madam.
Okay, sorry. Now, with a GNSS simulator or with any GNSS simulator, I'll be very generic. I will not go exclusively for Accord's GNSS simulator because it's a generic platform. I'll be giving you inputs on what exactly a GNSS simulator can do. And whatever I am showing here, Accord simulator is capable of doing. So with this simulator, we can generate and run different kinds of scenarios where a user can have complete control over what date, what time, and what location they want to simulate and validate that system, what kind of motion, whether it's a static, dynamic, aircraft, missile, ship segment. Ship segment. So different various kinds of vehicle motions can be simulated, different environmental conditions with different inotropo or the interference parameters, the signal errors and inaccuracies. If you see most of the receivers, they have a feature called RAIM. So if you have heard, RAIM is like receiver autonomous integrity monitoring. So because I told GNSS is a standalone receiver, it has to validate its own position. It has to give out information on the integrity of its position or the timing or the velocity solution. So inherently, most of the advanced receivers, they have a feature called RAIM. What does RAIM do is it tries to identify if there are any signal errors or inaccuracies. So a simulator will provide you options to add those errors, add those inaccuracies, and try to validate the receiver. And as I told you, different satellite configurations. In the live, you cannot switch off BDU and try to check what is your receiver performance. With a simulator, you can do any combination. You can check if I have only 3 BIDU, I have only 2 IRNSS, can I still give position? Or how feasible is my solution if I add one BIDU or if I add one GPS? So there are lots of satellite configurations that can be simulated using simulator. Now, just to give you a summary of, if somebody is trying to ask you if you want to buy a simulator and somebody is asking you why you want a simulator, this slide will definitely help you. So in terms of the common test parameters, the constellation signals, complete control is provided with simulator based testing. Environmental conditions, it is very limited in live antenna because you cannot control the environment. With a simulator, next, if we talk about repeatability, live antenna, it's not repeatable. Conditions are always changing. As I told you, satellite configurations are changing. Today you might have 8 and tomorrow it might have 7. But in simulator, you can fully repeat it and fully control it. External signals, in live, you might have unintended interference, FM, radar, or unwanted signals like multipath. In simulator, if you want, you can add. If you don't want, you can remove. So everything is under your control. Constellation errors. This is one of the biggest things that a simulator will help you. Is there is something called dilution of precision with respect to the GNSS errors. That is the error which is introduced because of the way the constellations are placed. Like I showed you that there are 6 orbits, there are 4 satellites in each orbit. So when each satellites are moving, at some point of time, they are so close that your dilution of precision is very high and you get a very poor positioning error. And those kinds of scenarios we can absolutely not test in live. But in simulator, you can try to do all kinds of circus. And as we have already spoken, high dynamics testing is very expensive in field, but it's very cost effective in terms of simulator validation. And new GNSS constellations, we can only test what is available in live, but with the simulator, present, future, and proposed, all the things can be tested if simulator is capable of simulating. So coming to details or specifics of a simulator input and outputs, it is very simple. Any simulator based on its capability or based on its feature will require the time at which you want to simulate, what is the reference file of the satellites which are orbiting the Earth, what are the atmospheric parameters that you want to simulate, any environmental factors, and the user position. If we give these inputs, a simple output from a simulator is an RF signal output, which will simply be connected to a receiver. A receiver would generally connect it to live antenna. Instead of connecting to live antenna, you simply connect it to a simulator. So the receiver will not know whether you have really connected to an antenna or a simulator. So it will do all the processing as though it is receiving live signal, so that you'll be able to validate it efficiently. Now, there are several features in a simulator that you might want to see based on why do I need this feature. I told you there are lots of receiver performance metrics. So how does those receiver performance metrics link to your simulator features? So any simulator, if it is providing a time configurability where it is allowing you to give different time inputs, it will help you to do lots of tests like the weak crossover test. You know that every week there is a week number. GPS is identified by week number and seconds. So whenever there is a week number change, does your receiver work properly? Or whenever there is a day crossover, there is something called day number in GLONASS. So when there is a crossover, is your receiver working? Leap second corrections. You want to check whether you're like, we have 18 leap seconds as on May 29, 2019. Now, if you want to check whether the next leap second correction your receiver is capable. So all these features should be available in a simulator if you want to do these kinds of validation. The second is the satellite configurability, wherein you should have options to select the user signals or for any kind of GNSS. Based on whatever is required, you can use it for your simulation. Next is the satellite orbits. Basically, if you see, we'll be getting online the UMAR, RINEX, AGL files for the satellite orbit and clock information. So your simulator should also provide features to load this data so that you can see which kind of data gives you better performance. As I told you, augmentation systems. So basically, SBUS has lot of messages and lot of information in terms of integrity and corrections. So if you want to validate your system for augmentation, both in terms of SBUS and DGNSS, your simulator should be capable of providing you customizable messages. So for the DGNSS also, we have several messages defined. So even those messages will help in receiver augmentation analysis. As I told you, the user dynamics. So the user should be able to generate different kind of trajectories, whether predefined or they can define their own trajectories for validation of the dynamics behavior. So a simulator, if it has a user dynamics capability, it will be really helpful for cost-effective validation. One of the major feature of any simulator, if it is available, is the hills. When we call hills, it is called hardware in-loop simulation capability. So hills is a feature which most of the commercial simulators, they generally don't provide, because this requires a very high-end capable processing feature of a simulator. So basically, if you see, this will be used whenever your GNSS systems are integrated into another system. For example, the INS, which is one of the major integration platform. So if you see, there is something called a 6-DOF system. So basically, this generates an INS equivalent data, and in real time, the simulator receives this data and generates the signal. So an integrated platform which also gets the INS data, also gets the equivalent GNSS data, and the receiver performance with integrated solution can be validated. So this is mostly used in ISRO labs or our RCI research labs, where they're trying to do a validation on the INS and GPS, and it has been very, very useful. Nowadays, most of the research labs, ADE, ARDE, so you name them, they are working on these integrated solutions, and this provides a very good platform for their validation purposes. Next is logging of the simulator data. Like, I know what I have simulated. If I log those data, I can compare it with the receiver performance, receiver log against the truth, and try to do a complete validation of your receiver. And also in simulators, we generally see different modes of simulations, wherein normal is like it works like a real-time simulation. You click the run button, it will behave as though live antenna signals are being transmitted. Second is, we generally provide an option called virtual scenarios, wherein you can try to do the scenario validations. If you want to create UMT files, the user motion trajectory files, or it will also give you analysis. What time do you want to do live antenna testing? What time is the best time where I can get maximum number of satellites, or which is the best day where I have minimal interferences? So this will be helpful in terms of the trial time analysis. And as I told you, if I have to synchronize my systems with other systems, I also have to provide a trigger mode of simulation, which will help you to synchronize with other systems during simulation. Next is the signal and channel configurability. So if you see here, most of the GNSS constellations, at any point of location, you will minimum have 8 to 10 satellites. Now, what if among 8, only 4 are working, or among 8, your antenna is very bad and you're getting very low signal strength on few satellites? So if you want to do different kinds of analysis, this kind of features, wherein the signal control feature will facilitate you to do GNSS signal fluctuation analysis or cross correlation analysis, where one signal is at very high power, the other signal is at very low power. What is the effect of this cross correlation? And if you're trying to develop some cross correlation algorithms to improve the cross correlation effects, this will definitely help you in terms of your research. Similarly, we can also add lots of errors for multipath simulations or urban canyon simulations. You want to include, exclude. And as I told you, error models is one of the biggest contributing factor for the GNSS accuracy. So any simulator should provide you all the error parameters in terms of atmosphere, satellite orbital errors, or the clock errors, the clock noise errors on both satellite clock, receiver clock, or the anomalies. When we talk about anomalies, we generally talk about the step errors, ramp errors, or the Doppler offset errors, which are intentionally added to check the range performance of the receivers. Also, we have generally every simulator will have its own add-on configurations. So some of them are mainly highlighting is our NavIC message scheduler, because NavIC transmits in its subframe 3 and 4. NavIC has 4 frames. 1 and 2 gives you the ephemeris data. 3 and 4 is reserved for all your almanac and other additional messages. Like if you are giving your IRNSS receivers for maritime applications, where you want to alert the fishermen on some safety messages that has been broadcasted on IRNSS, you can do those messages transmission here. You can customize those messages intervals and try to see how effective your receivers are. So this is just one example, but you can use the customizable features of any of these simulator features for your own benefits. The last feature is the antenna characteristics, and not just the receiver performance. The receiver performance is also dependent on how good your antennas are. However, the transmit antennas are fixed on the satellites. We cannot change that. But the receive antennas, we can always validate in terms of its gain and phase. This is very much helpful when you're doing code carrier based receivers for high accuracy applications, wherein your receiver antenna plays a very important role. So if you want to validate your receiver antenna performance, you can load in the receiver antenna characteristics here. We simulate those satellite behaviors based on this antenna, and we can see how good the receiver performance is. Now, coming to the last part of our simulator, till now, what we discussed was the features of the simulator or the receivers and how to validate them. So, this is a summary of the GNSS simulator pioneers in the market. So they fall under 3 categories, like the component manufacturers who manufacture the GNSS simulator in a standalone sense, or the system integrators who work with an integrated setup, or there are other simulators or extension of the existing simulators which provide you value-based service providers. So if you see here, there are lots of simulator manufacturers in the world. So, but if you see in the entire list, Accord is the only Indian company which provides the GNSS simulators for our Indian market. And there is lots, Aurelia, iPhone, Spirent, Microwave, Cast. So there are lots of simulator manufacturers, and they have their own way of using the simulators. Either it can be standalone or integrated, or as recently as using it for connected car validation. So you see here that driverless tracking or driverless car navigation. How do we do that? It is basically used on GNSS, one of the GNSS features. So integration of that and validation of that particular entire system setup is provided by Safran, one of the leading manufacturers of simulator. And as I told you, anti-jamming, anti-spoofing is one of the biggest threat for GNSS. Now, how do we validate? One of the major thing is controlled radiation pattern antennas. So there are simulators which provide you applications with respect to CRPA testing. Two of them I have listed here, Spirent and Cast, but there are others as well. If you want a low cost solution, you also have something called LabSet, which is a small portable. It is simply a record and replay. You cannot go to a field trial every day. You cannot take your van and run through. So you go there, record it once, and you come and replay in the lab to try to do the validation. So there are different kinds of simulators available in the market. I have just given you a summary of how the simulators would be in future. So if somebody is interested to develop a simulator, they definitely have a good market. So if you see, it's in millions, and it is just growing. There is no way that it is going down. And this is actually a research by GNSS Simulators Market, a lead market research who do research, yearly research, and also publish their data in GPS World magazine as well. So anyone interested can always follow them. So you can get yearly data on this. And last but not the least, I would also like to introduce our own simulator, Accord's indigenous simulator. We call it as SIMAC6. So this is many constellations, one solution simulator. We are a configurable dual frequency GNSS simulator. So you name the constellation, we have it. You name the frequencies, we have it. GPS, GLONASS, Galileo, BeiDou, NavIC, SBAS. It supports all the SBAS signals. We have the processing capability, whatever I mentioned till date or till the last slide, capability of a simulator. We have that in our simulator. If anyone is interested, they can always contact Bharti. He can provide you further data on this. So this concludes my presentation. I'm sorry if I have rushed through the presentation. Because of the time limit, I had to just quickly run through my presentation. I'd be happy to take any of your questions.
Participants, any question?
Madam, good evening, madam.
Good evening, sir.
Madam, is it possible to do this data fusion technology with the help of this GNSS simulator with the help of best available satellites among all constellation?
Yes, sir. That is definitely possible. Generally, all the receivers in the market, if you see, they give an integrated solution. GPS plus GLONASS, GPS plus Galileo, GPS plus BeiDou. So based on the, as I told you, they generally have RAIN features. So it validates the integrity of each of the solutions and try to see how we can combine them to give an improved position, sir, or improved solution, whichever is the solution from the receiver. That itself is a research domain, sir.
Thank you, madam. Thank you.
Any other queries? Good evening, participants. It is my honor to deliver the vote of thanks for today's enlightening lecture. On behalf of our department, I extend my heartfelt gratitude to our esteemed resource persons, Dr. Pratibha and Mr. G. Bharathidhasan, for taking time out of their busy schedules to address us. Ma'am, your presentations were highly
Ma'am, I think you're muted.
sorry for the interruption. It is my honor to deliver the vote of thanks for today's enlightening guest lecture. On behalf of our department, I extend my heartfelt gratitude to our esteemed resource persons, Dr. Pratibha ma'am and Mr. G. Bharathidhasan, for taking time out of their busy schedules to address us. Ma'am, your presentations were highly informative, thought-provoking, and inspiring. The valuable insights you both shared have broadened our understanding and motivated us to explore more deeply. I would also like to express my sincere thanks to our principal, head of the department, faculty members, and coordinators for organizing this session and providing continuous support. A special thanks to all participants for your active involvement and enthusiasm, which contributed greatly to the success of this session. Once again, we are truly grateful to Dr. Pratibha ma'am and Mr. G. Bharathidhasan for their meaningful contribution to our learning. We look forward to the opportunity of welcoming you again in the future. Thank you, ma'am. Thank you, sir. Thank you, everyone.
Thank you all once again.
Thank you all. Bye bye.
Participants, please wait. The next section, the resource person is going to join in a while. Please wait. Good evening, sir. Are you able to hear my voice? Raju, sir?
Yeah, I can hear your voice. Can you hear me?
Yes, sir. Yes, sir. Okay. Good evening, all. Um, it gives me immense pleasure to welcome you all to this faculty development program. At the outset, I extend a warm and respectful welcome to our distinguished resource person, Dr. G. Raju, a visionary scientist whose contributions to India's space-borne microwave remote sensing missions have been truly extraordinary. Dr. Raju sir began his career at ISRO Ahmedabad in 1972 as a microwave engineer and played a pivotal role in developing India's first microwave remote sensing payloads, that is called as SAMIR, on board the Bhaskara 1 and Bhaskara 2 satellites. His international research presence is equally inspiring, from serving as a visiting scientist at German Aerospace Research and Test Institute, West Germany, to contributing as a project manager and associate research engineer to the Antarctic Radar Project USA, and completing his PhD at the prestigious University of Kansas, USA. His development of the coherent Antarctic radar depth sounder, a synthetic aperture radar for ice probing, which he field tested in Antarctica and the South Pole, stands as a testament to his innovation and scientific excellence. Dr. Raju sir is also an IEEE Life Senior Member, Fellow of IETE, and distinguished academic, guiding numerous of PhD scholars at Jain University after retirement from ISRO. Sir, your presence today is privilege for all of us, and we are eagerly looking forward to your insights, which will undoubtedly enrich our understanding and inspire our academic pursuits. I also extend a warm welcome to our respected principal, sir, head R&D, sir, HOD madam, faculty members, participants, and everyone who has contributed to organizing this FDP. The session is yours, sir. I will share the screen, sir.
Okay. Good evening to all of you. Am I audible?
Yes, sir. You are audible, sir.
Yeah. I thank you, Mr. Dr. Mukesh, for introducing me to the faculty who are attending this FDP program. And it's my privilege to talk to all the distinguished faculty who are gathered today for this particular particular program, where I'm going to talk about India's as well as the global navigation satellite systems. Very important for us today. And also, I'm sure you are aware of the various achievements done by India's NavIC mission during the recent conflict, both in terms of approaching the target as well as in improving, establishing our credibility as Atmanirbhar system, Atmanirbhar capability in developing our own GPS. So in this context, I would like to also bring what is happening today. Recently, we all know that most of the airlines are grounded. I'm just telling you about the possibility of, there are two kinds of worries about this. One group, one theory is that there was a solar storm. Solar storm means it will really distort all the electronics hardware. So one group of people have already corrected all the A320 softwares which are affected with solar storm, number one. Number two, there are occasions where the adversaries will actually try to disturb your GPS position. GPS position is very, very critical, especially in the warfare games. And we are happy today that we have our own indigenous GNSS mission known as NavIC system. And I will touch upon NavIC as well as a general introduction to global navigation system with specific emphasis on the differential NavIC. Normally, a GPS system is credited, or how do you measure the performance of a GPS based on the accuracy of position determination. So I will generally go through all the basic elements of GNSS mission and come to the concluding part where I will also touch upon the differential NavIC system equivalent differential DGPS, if it is GPS, where the accuracy is very much improved. Of course, there is another program, another session where my own friend, my own colleague, my student, I should say, will be talking about his own performance during his research on this differential NavIC. And so I will not elaborate on that, but I will certainly touch upon those things. You will be hearing from him on Friday, on Friday. So let me start with the basic system. What is meant by GPS? All of you, without exception, all of us are using GPS. What for? All the people today who are using smart mobile phones are aware of using the importance of using the GPS for many of your direction finding requirements, like hailing a taxi or finding a position when you are traveling, when you are finding a difficult unknown places, unknown people, want to get guided. One with GPS will certainly guide you in all the occasions. And also school students, transporters, tourists, trekkers, people on picnic, including such people, even the less knowledgeable people like taxi drivers and many more. They know very well GPS provided, they use the GPS provided directions for their movement. It's a very essential part of our life today. Of course, we have started with the aircraft, satellites, ship, weapons, guided missiles, very advanced demands for guiding the missiles using GPS. A GPS will be mounted in the nose cone of a missile to look at possible targets and guide the missile to reach the target. Next one, I will request one by one, next slide like that. Mukesh may probably. So, why do we use navigation? Long back, we had a problem of, we were guided by the star, galactic navigation using the North Pole. Using the, pole star, I should say. Navigation is needed for monitoring and controlling movement of a mobile object. When I am moving on the ship, on the land, on the aircraft, or anywhere else in space itself, even when I am launching a satellite using rockets, I need a GPS direction finding device. Today, we are able to keep a indigenous NavIC. Any question? Are you able to hear me?
Yes, sir. No, sir. Small interruption. Please go ahead, sir.
Okay. So what I'm trying to say is essentially it is being used even for monitoring a satellite movement sitting on a rocket. That is latest achievement by ISRO's NavIC. It has been put on the rocket. It will monitor the movement, for example, solar panel opening, how it is progressing in space. All these things are very well possible due to the application of GPS or in general GNSS mission. There are 4 categories, as I said: land navigation, where you want to look for if you are transporting very you must know. For example, in the US, the first very strong application began monitoring the UPS van. UPS is the United Parcel Service of the US, where they were monitoring because a lot of commodities, valuables are in the van. So they want to make sure everything is properly guided and the van is moving safely and without any pilferage or any kind of a difficulty in movement. That is mostly land. Marine navigation, ships movement, and any kind of demand for unknown, because there is no landmarks. When you are going on the ship, there are no landmarks. Maybe you can get some galactic support. However, very difficult to have on ship, but you must have your own navigation system, which is done by the GPS. Then aeronautical. Today, as I told you, we are very much dependent on the GPS and space navigation. Position determination for space, we have been using also for location of the satellite position is by ground-based control points. But now, if I put a GPS on board a satellite, it will tell very exactly where the satellite is moving. Of course, it should have, essentially, it must be able to see minimum 4 satellites, minimum 4 NavIC kind of satellites or GPS satellites to identify its position. I will explain the principle of why 4 generally. Please go to the next slide. Before going to the theoretical aspects, historical, as I said already, people moving on the seas they used global navigation satellite, the galactic movement, galactic observations, like the pole star. Today we have, in general, globally, we call it global navigation satellite system, and we have our own navigation satellite system called NavIC. NavIC is a abbreviation for navigation with Indian constellation. So apart from the position determination, there are offshoots of many other applications. For example, the space weather. What is space weather? Ionosphere. Ionosphere disturbs the communication on ground. Ionosphere disturbs the ground power grids. So we have to study ionosphere using some techniques of the GNSS mission, which is built for position determination, but incidentally, it's another application for space weather, ionospheric research. Then remote sensing application. There are also some new application looking at Earth from space, GNSS interferometry, GNSS agriculture, GNSS farming, all those things are new developing areas where GPS or GNSS missions, including NavIC, are being very well utilized. And one more thing is GPS is also used for studying the another way of looking at the atmosphere is GPS occultation. What is GPS occultation? We have many GPS satellites or ISRO's, India's NavIC satellites, and we have satellites mounted with a GPS receiver on our own remote sensing satellites. When the satellite signals, which are far away at 20,000 kilometers, and our low Earth orbit satellites are around 1,000 kilometers, the line of sight cuts through the ionosphere. That creates a kind of delay. So we'll see that also. That's called occultation study. That means Earth orbiting satellite will disappear. That is, when they come behind the Earth, with losing sight of the GPS or NavIC level of NavIC satellites, they cut through the ionosphere or troposphere, and that's indirect way of probing the ionosphere and troposphere. These are all additional advantages which are not really decided. Basically, it was decided for position determination. So we have the additional thing decided by the, what I was just now told, space weather. Space weather is very important because you know that space weather normally is affected by intense solar radiation. When the solar radiation is having very strong observation, very strong emission, it may even kill satellites. So, for example, Aditya L1 is looking at the geomagnetic storms that are happening, and by going close to that. So these are all some of the applications in I'm adding a few things for today. Sometimes you will have a blackout. Some of the satellites, like for example, some of the satellites died. So what is the way, if you know that by the time the radiation reaches your satellite, you switch off the satellite for some time, you switch off so you are safe. Otherwise, they will disturb all your digital circuits. So, it is historical perspective. That's what I told. Position fixing. What is position fixing? To enable a navigator by knowing a particular already recorded location, like a ground checkpoints. Say, for example, you are going to your home and say, if somebody want to guide you, say, my house is next to the coffee day shop or whatever it is. That is a known way of looking at it, very, very crude and very conventional way. So, celestial navigation is another one where you have used the distant celestial object is used as your direction finding device. Next one. So, what is celestial navigation? We go through a very different kind of coordinate systems. When you are in space, you have to follow another set of coordinations is coordinate called celestial coordinates. It is this picture clearly shows Earth rotating in a big, infinitely large radius celestial sphere. Mostly this coordinate system used by the astronomers to define their position. So this is a convention I thought I should bring out. The term celestial sphere and celestial navigation, celestial coordinate systems. Next one. So in astronomy and navigation, the celestial sphere is an imaginary sphere of arbitrarily large radius. All objects in the observer sky can be thought of as projected upon a surface, inside surface, like you see when you go to the, for example, so some of the place, I don't know whether you are aware of some of the, how do you identify the galaxies? You have to have some kind of a projection to look at the stars or the galactic constellation you have, and they are projected on the inside surface of that sphere. The celestial sphere is a practical tool for spherical astronomy. only for you to know more about that when you are serious about astronomy. And next one, please go to next one. This is the celestial coordinate system, nothing different from the normal thing. Now I have told you in this particular thing, North Galactic Pole. This pole star is a reference, and we have with respect to pole star, we have with respect to the next one, please. The global. I'll come to the global coordinate system. The other one, what is a pole star? I'll come to in the next few slides later. Global coordinate system. Suppose you want an image of a particular location. You want it from a particular location on Earth. We have to define, obviously, the coordinate system, latitude, longitude. That's all. Here we have the same kind of demand for looking at the space. In space also, we have to have a kind of coordinate system similar to geo coordinate system. Next slide. I'm just giving a very simple location of what is Polaris. Polaris is a dual star, Polaris A and Polaris B. Next one, it is the Ursa Major is a constellation. The tail of the Ursa Major is a 7-star constellation as shown here, and Ursa Major, Ursa Minor. So there is a definition of what is Polaris here. As you can see, the red dot. Next one. So this constellation of Ursa Major and Ursa Minor will bring out a very closer view of the so-called Polaris. Polaris A, Polaris B. As it is shown, Polaris AB, Aldebaran is a star. And for you, for a little bit more detail of that particular star. Next one. The still closer view, the brightest Polaris A is your pole, which is available, which is very, very, very far. And wherever you go on Earth, the latitude you can easily identify. How do you identify pole star? You raise your eyes towards by an angle equal to local latitude and turn yourself towards north. I'll repeat it. If you want to identify in a clear sky where pole star is, you raise your eyes by lifting a degree, an angle equal to local latitude. You see the red star, which is very, very still, very far away, a good reference for our navigation. Next one. Now, when I'm talking about position determination, earlier, before we are thinking of GPS or GNSS, people are measured by using LIDAR. What is LIDAR? Light detection and ranging. And they have been able to find out the distance of the moon with a very high accuracy. And they have determined that moon is moving away from the Earth by 1.5 inches per year. This has been detected by what is known as laser ranging experiment. And also, we have done, next one, this experiment has also been done by the Apollo astronauts. See, I'm trying to bring out the issue with respect to position determination. Other methods are also there. That's why I want to connect you with this kind of measurements being done in general. And they have put a reflector called retro reflector. Louis Armstrong and his team, they put the reflector on board the moon surface and sending signal from ground to moon and back. That determines the distance of the moon, and that is how they have been able to find out how far is it moving farther away or not. This is astronomy, and other things are all lower. From ground, you can have powerful telescopes, but in addition to the telescope, the laser ranging LIDAR has been used for determining the position of the moon. Now coming back to this is about slightly away from the topic. Please, next one, Mukesh sir. So what is global constellation, global positioning system? As the name says, complete global coverage with the 24 satellites. Why 24? The GPS satellite, GPS constellation, as you know, is a US made versatile equipment, versatile support for finding yourself on at any part on the globe. That's why it's called global. Global, whereas compared to ISRO's NavIC, it is Indian regional. We are not going for global, but it is regional navigation satellite system. So there are 24 satellites in 6 orbital planes to facilitate covering the entire globe for identifying yourself, whether not northern hemisphere, southern hemisphere, North Pole, far away places. So this is a very powerful mission, already working on that. Next one, please. What is the purpose of GPS? How does it work? GPS answers, where are we? As I told you, trekkers, people going on hiking, they are lost. There is no landmark. There is no way of finding out yourself. It answers, where am I? Latitude, longitude, and elevation. If you also have a proper map with you, you can yourself find out where you are and what altitude you are. Secondly, where are we heading towards? If I am going on a mobile platform, successively I will find out the position by using the velocity of successfully detecting my own position. I'll know where I am, in which direction I am going, because the positioning is rapidly complemented by the GPS. Every 1 second, please remember, every 1 second, you will have the update on the positioning by the GPS. Next one, please. So GPS, about GPS, a few topics, a few things about GPS. GPS is a 24 constellation, as I showed in the picture. It is used for GPS ground station. See, these are all the things which have been already established during the military requirement of NavStar mission. Started with NavStar. Naval satellite missions required for the US Navy. Now, GPS is an extension of the same for global application. So, today we are able to find out not only your position in latitude, longitude, but altitude, but there is a way to determine 3D positions, 3D position of a particular place. Accuracies are very good. Meters or sub-meter. Please note that our GPS, what you're receiving, what you're operating in your mobile phone is not yet having our NavIC chip. So we are still dependent on the GPS, global positioning system of the Americans. Why did we? So the accuracy available to us is 5 meters or so, whereas for the American forces it will be sub-meter level. Sub-meter level accuracy is available for the Americans. Now coming to, it should be, when I'm developing a system, what are all the expectations? It should allow multiple users, unlimited users. They should be able to receive. That's why I said we have to have 24 we have 24 satellite. We are dependent on the GPS so much that there is already a hot redundancy. I will explain to you in the next few slides that minimum 4 satellites are required for determining your position, because you have to you need 4 unknowns. 4 equations are formed by using 4 satellite positions. Please remember, there is not big mathematics here. Simple equations. You are from your mobile location, whenever you are looking at 4 satellites, there are ways of determining your position by what is known as trilateration. And there are 4 equations that can be found by 4 satellites. What are all the 4 unknowns? X, Y, Z, or latitude, longitude, altitude, and the time. So these are all the things that you demand. So I want real-time position for navigation. It's very important if it's particularly for mission, for the aeroplane or even rockets, satellite movement. It should also available for it should be what is known as jam proof. When I'm using it for my satellite, my application in military, of course there are mischievous users also. We cannot help it. Anti-jamming device. Now there's from 2000 onwards, the jamming is not allowed. That's a worldwide accepted in principle accepted by everybody on it, because GPS is, it can be, if your GPS can be jammed by using some electronic countermeasure. So whenever you design a system for civilian applications, should be jam proof. There is a way to avoid this, because all GPS frequencies are all well defined frequency bands. You cannot use whatever way frequency you want. There is a frequency coordination committee, like in any communication system. Even for a navigation system, we have a coordination committee worldwide, not to allow unwanted, only specific users. So this is one of the requirements of the GPS. Now next, let us how GPS or next. There are, suppose you are receiving a signal from a particular satellite. One satellite will tell you, I am at this location. He knows, the satellite knows my location. You get from the satellite, you get 3 parameters. One, its location and a code and the time of transmission of that code. Please remember 3 parameters. My location, that is satellite location XYZ, and a code which is known to you, and the time of sending that code. And you receive that code. You receive that code and say, okay, I received at some delay. The satellite says I sent a signal at T1, and you received at a delay with a delay of delta T1 from satellite 1. So I know the position, I know the distance by simple equation. S is equal to Vt. V is the velocity of light. That is S multiplied by delta T, time of propagation. How did I find the time of propagation? The satellite told I sent it at this time, and the receiver detected, yes, I received at T2. So I have measured delta T. So timing is very, very important. I'll come back to that a little later. So, but I don't know from where. It can be from a sphere of that distance. Suppose it's at 10,000 kilometers, I find out. But from which direction is not known. If I have second satellite, I can slowly come to a common next one. As you can see here, the common intercepted volume as shown by the D1 and D2 referred. I mean, there's a reference for D1, reference to the common intercepted volume will be the position. But still you are not come close. Next one says, if next slide, please. If I go to 3 satellites, then my plane, my reference will come to smaller volume. So 3 spheres, there are 2 common points of intersection. So we have to have a third one, and these positions will be, so minimum 3 satellites are required by simple equation. I will explain the next one, please. So this volume reduces closer and closer. If I have 4th one also, I'll get still better one. Next one, but it's not essential. Now, there are the receiver uses messages received from the satellites. What are the messages? I sent a code at this time, and I am at this position. So you are able to receive with a delay of delta T1 from satellite 1, delta T2 from satellite 2, delta T3, satellite 3. Next one. So I have the problem. How do I define the problem? I want to determine X, Y, Z, and B. What is B? B is the time delay, time taken, and X at what time? At the time B, I am at X, Y, Z. At a different time B2, I may be at X1, X2, Y2, Z2. So this is the simple equation. We can form a 4 equations which can be solved for 4 unknowns. 4 unknowns are X, Y, Z, and B. Next one. So whenever we have these 4 equations, we get what is known as pseudo range. Pseudo range is nothing but, the word pseudo means false. Why do I call it so? You can, as you can find out, the position P is given by the time difference multiplied by velocity, and this is given by xi, yi, zi for position I. So why is it called pseudo? Is because it is not a geometrical distance from the satellite to my place. It is distorted by propagation. As I said, propagation through ionosphere, propagation through troposphere. There can be many other errors. So that's why it's called pseudo range. Next one. So this is, hopefully you have understood the basic principle, that is to determine my position, where I am having in my hand my mobile, I must have minimum 3 satellites visible, 4 satellites. You may be experiencing in your own practical way of you are using left and right your as a mobile, and you will see, so you will get sometimes GPS loss, not GPS visit, no, not all required GPS minimum 4 are not available. You will get the signal also, and it will also say GPS lost. Suppose you are going in the underground metro or someplace where there are too much of blockages. Then you will say, well, GPS is not visible. So the accuracy is very poor. These are all practically you should have experience, I think, that why that happens is because I'm not able to, suppose I'm going in a dense forest. Though forest is supposed to be allowing propagation of electromagnetic signal, very dense forest, I may not be able to get all the 4 satellite visibility. So these are all the few problems what we have. Now coming back to what are the GPS components? When I say GPS doesn't work with only your receiver, as I said, space segment, that is one part of the story. Control segment. Why control segment? As I said, each GPS satellite will tell you where I am. That means my coordinates should be tracked by a ground-based for accuracy. Although onboard systems will tell you where you are in terms of satellite position, ground control systems will also correct all these satellite positions. So I'll explain to you a little bit later more functions of the control segment. Then user segment. We are the user segment. I and you and other people who are using the application of mobile. We are the user segment, which is a very compact tip. Unfortunately, though we have done the space segment, that is IRNSS or NavIC mission, entire mission is ready, but ground segment is still going on. Hopefully in the next, very soon, we have collaboration with foreign companies, and there are very powerful companies like Qualcomm. The purpose of developing it is easy to develop a system, but you cannot develop a compact chip called chipset, which should go into your mobile. That's where we are still held up. But of course, with the government spending a lot of money, lot of investment on the chip semiconductor industry, we are sure to get our own chip making companies in India. Next one. So all this space segment is, as I was told you, is nothing but 6 orbital plane at 55 degrees. They are nearly 12,000 miles or 20,200 kilometers. You must probably have people who have studied medium Earth orbit, especially for GPS. That orbit is decided because in that orbit, all the satellites should keep moving to cover service for global application. And LEO, low Earth orbit. Low Earth orbit for your monitoring, weather monitoring, going around the Earth using remote sensing like a radar or camera or whatever that LEO. But this, why I told all the MEO is the orbit that is called medium Earth orbit, about 20,000 kilometers, where you have these 24 satellites. Next one. Now, as I said, control segment is not just for positioning information. They should keep on controlling and monitoring the position accurately, so that whenever the satellite will keep on giving broadcast signals, and we pick up from the ground. Whenever it is broadcasting, it should tell its position accurately. So for that, the ground support, there are 5 monitoring stations. Am I audible?
Yes, sir. Yes, sir. Please, sir.
There was some interruption. I thought.
Yes,
Okay.
yes, sir. Yes, sir. Correct, sir.
Okay. All right. Now, what I'm telling in this slide is, are you able to read the slides? So, under the Department of Defense, there are many ground stations, particularly 5 stations, because they have to globally cover monitoring and tracking the MEO satellites. Colorado Springs, Ascension Island, Diego Garcia, Hawaii. These are all the 4 or 5 stations which are globally monitoring these 24 satellites, making sure they are on the right path, right location, with right information. And those data are supplied to the satellites, and the satellites will broadcast. Please note that these ground stations will transmit, number 1, their position more accurately to the satellite. Satellite will determine its own position, but more accurately, we have more sophisticated system from the ground. They will determine with a very good accuracy. They will determine, the ground stations will determine the position of all the satellites. There is one more function which I will come a little later, that is about the timing. Next one. Okay, now I told you that the frequencies are all very well allocated. You cannot use whatever frequency you want. World Administrative Radio Committee under ITU has to allocate frequency for you. In the case of GPS, L-band. What is L-band? L-band is 1 to 2 gigahertz. All of you must be knowing about the designation L, S, C, etc. L is 1 to 2 gigahertz. Why this frequency? Because at this frequency, the atmospheric attenuation is very, very low, and they can penetrate the vegetation, like forest or any kind of canopy of the forest, leaves and branches. It can penetrate from 1 to 2 gigahertz. So GPS has got 2 different frequencies known as L1 and L2. The power available is a technical data available, but here I want to say one important thing. The code is called C by A code, that is course access, for available for all general purpose civilians. P code is the one which is called precision code, not to people who are familiar with digital communication. Maximum seek long codes are used for precision coding, which is not available to us. So for the military users, defense applications, the available code is called P code, precision code, whereas for the general purpose civilian application is called C bar A code, course application. Okay, course available. So there are, as I said, the next one, navigation message. Navigation message is a very, very small bit rate. 50 bits are enough. You're only sending latitude, longitude, and a code which is about a kind of code, precision code for the defense people of the US. And same thing for NavIC. NavIC will give you what is assured in NavIC is about 20 meters, but we in Jain University have made measurement up to even 8 meters. And for the defense forces for India, it will be less than a meter. Again, same theory. Code is different for military applications, and code is different for military applications. So it's called PY code. Next one. So this is the way it is more of a technical details. A stable atomic important point I want to make here is whenever I am sending a signal, whenever I'm sending a code or even timing information, it should be very stable. If it is not stable, my measurement will go haywire. So I should have an atomic clock. I must have an atomic clock. For example, when I am sending the signal from there, I send this signal at this time. Unless you have a precise atomic clock, you cannot have good, precise position information. So just this is for general application. We have a frequency of atomic oscillator about 10 megahertz, just for information only. Next one. So what is the seriousness of GPS? What are all the errors? There are many errors. One is I just told you about the atomic, the timing error. But there are many more errors available, that are possible in the GPS. Minute inaccuracies in keeping time. See, you have a watch. You get normally in the PNT communication group, used to send us time now is. I don't think that comes now. Long back, earlier days, we used to correct our watch with a second accuracy. But whenever you are talking about the accuracies of GPS demand, it will be in terms of micro or nanoseconds. So satellite orbits are also one of the errors I have told you. Satellite orbits are drifting. That's why ground-based orbital determination is very, very important. That will be one of the causes of errors. The first one I told you is timekeeping. Second is knowledge of the orbit. As I said, 3 different messages will be sent by the GPS satellites. One is the code itself, timing information at what time this code has been transmitted. The third is, where am I? Where is the satellite? That is the orbital location of the satellite. Then you have uncontrollable atmospheric errors. You have got, as I told you, it is minimized by using the frequency of L band 1 to 2 gigahertz, where the atmospheric losses are very, very reasonable or practically nil. So what is the cause of, what does it affect? If I send a signal from the satellite to ground, my main dependent parameter is the time delay. So the troposphere, water vapor, liquid water, clouds, etc., contribute unwanted delay. Any coarser medium to denser medium, very rarer medium to denser medium, if you are transmitting, there will be a refraction. That means this straight line path is not being taken. It is bending. Electromagnetic waves are bending. So what happens? As I said in the earlier slide, this is a pseudo range. The range is not accurate, caused by the atmosphere. Of course, this is minimal, but still it causes some errors. Of course, there are methods to correct it. That's what we are going to talk at the end of the lecture. That is by differential positioning. The other one is the other one is the ionospheric delay. Ionosphere is very, very difficult to control. Ionosphere, we have no control on that. For example, when the normal total, the ionosphere is decided based on total electron. How do you define the ionosphere? Ionospheric content is, if you take a volume, vertical volume, a cylinder from here to space, the total electron content, number of electrons per meter square. Number of electrons per unit area is called total electron content. So this varies over a period of 24 hours. Why? When there is a sunlight, sun ionizes the atmosphere or the particles in the atmosphere. So more ions are formed by about 3 o'clock in the afternoon, where the ionosphere gets heated up. But as the night arrives, the atmosphere cools down, number of electrons recombine. Most of you who have studied radio communication know about the F layer, F1, F2. Two layers are the one used for radio communication. F1, F2 get combined, called F layer. But they split into F1 and F2 due to ionospheric effects. So the error can be like total electron content may vary as high as 2 to 300 or even 1,000 times. Number of electrons in a particular volume can be varying from one end to another end, from the beginning, when the early morning to late afternoon, it can change by 1,000 times, worst case. Apart from that, there will be solar flares. Solar flares which affect immense radiation, causing lot of electrons, plasma, and they affect your communication. Not only communication, they affect your ground power grids. There have been cases. There are that the intense radiation from the from the sun affects communication. They come power grids. They affect the GPS. We are talking today more of GPS by causing large delay. When I know the delay is affected by the solar flare, what does it mean? My total electron content has changed, and so my pseudo range has increased. So my accuracy of time is gone. So this is the way we have to worry about. One of the errors is by the ionosphere. Next one. So I think Mr. Mukesh, can you give me 5-minute warning to when I have to complete?
Sure, sir. I will do it, sir. Please, sir.
We are still in good shape.
Yes, sir. Yes, sir.
Yeah. Apart from these two, tropospheric error, ionospheric error, I'm talking more about the errors because how do I overcome by using differential technique? Finally, I'll come to that. And multipath error. Suppose I'm in a building complex where there are tall buildings. So the signals from satellite go and hit the satellite. I'll have a direct path. I will have a reflected path. I get confused. Your GPS receiver gets confused. I'm getting not only one signal, more signals. That's called multipath. It cannot be solved. Please note that this is still a problem. There is no solution yet. But having more number of satellites is one way of reducing, optimizing the signal, the loss of signal or path distribution. Then there are errors caused by your own receiver. Your receiver has got a limitation. Your receiver has a crystal oscillator. I cannot have an atomic clock in my receiver. It's a very huge. So receiver clocks are one of the culprits contributing to the time error. So internal, and also as I said, spoofing. What is spoofing? When I'm having a time factor very critical for me, as I told you, from the satellite to my receiver, I have to measure the delta T. But sometimes deliberately for the defense people to as it's a mischief, it's not allowed. It is not allowed, it's against the norms. They introduce unwanted delay so that you are confused. I would like to mention here, why did we go for NavIC when GPS is available? During the Kargil war, we were not supported suitably by the GPS. We faced problems. So we had to suffer. Whatever be the way of suffering, because we were directed to wrong places. Because what is the position of your military? He has to know where he is, where his soldier is. All these things were disturbed by what is known as spoofing. That is the source of our government going for NavIC. Not only us, but there are 6 other missions, which I'll tell you. GLONASS, Russia. Galileo is Europeans. Baidu is Chinese. India is IRNSS. QZSS is the Japanese. because everybody is worried about their security. So these are all the things which are banned by what, that is selective availability. SCA means you are deliberately adding some selective places to confuse by increasing the delay. But though it is allowed, though it has been discontinued, still there are mischief going on in the global military warfare. Next one. Continue. Okay, I just want to tell you how serious is the error, clock error. One of the examples, serious errors is, as we cannot afford a clock, atomic clock, and what will happen if I have an error of, if I have some error in the range. For example, one error, 1 second error leads to very, very serious. Of course, we don't encounter that. What is the speed of light? 3 into 10 power 8 meters. That is the error. If I have 1 millisecond, I have 300 meters error. If I have 1 nanosecond, 0.3 meter error. So my goal should be as close as possible. I must approach 1 nanosecond error or even 1 picosecond error. That should be the goal of a very good position determination clock. Okay, so this slide brings you importance of clock accuracy. So how do you take care of this? I cannot afford a very powerful clock even though I have got a very good atomic clock on board, we still depend on ground-based clocks transmitted or broadcast from ground. For example, we have what is known as National Institute of Standards and Technology, NIST, in Boulder in the US. This is for the GPS. As of 2013, we had a very powerful CCM clock. That is, it has an accuracy of 3 into 10 power minus 16 seconds. Please imagine this is a very, very powerful, very, very accurate. What does it mean? I lose only 1 second or 2. I lose or gain 1 second, 100 million years. Just to give an idea of clock accuracy available today from various countries. In India, we have a CCM clock. In our ISRO's ISTRAC ground station, known as IDSP, Indian Deep Space Network, IDSN, in a place called Bailalu. I don't know whether you know about this. If your college, your department permits, you please visit these places. Very powerful ground station clock. It gives a very powerful, very accurate satellite timing information. So what will I do with this timing information in general, whether I have from NIST or anywhere else? That keeps on broadcasting timing information from ground. All the 24 satellites, they pick up that number, that accuracy, they reset their watch. You reset your watch, the satellites reset their clock. So when the satellite gives you the timing information, it will give you a corrected timing information as provided by the updated information from the ground. So this is another one which I was telling you, all those 5 different stations on the ground, apart from controlling satellite position, they give the timing information to the satellites, all the 24 satellites. This is a very important support. Otherwise, you cannot achieve our very accurate positions. And I have given you one picture here. Look at the huge structure where this official time is given by this atomic clock, which will lose only 1 second in 100 million years. Next one, just for giving an idea. Okay, now I talk to you about user segment and control segment. User space segment, I told you, that is the satellites with various parameters. And I would like to explain to you here, we have Yeah. We could not get very powerful, very stable, clocks from US. So we had to go to the other countries because it's a very important, confidential, very difficult to get this atomic clocks to be given to another country because it's my property. I don't want to give you, and that's how we went to Swiss. Switzerland is very good in clock making, and they have got very good atomic clock. We went, and so we had to face some failures. They are not as good as what they have in the GPS satellites. However, we have. I want to inform all the people here that ISRO India is now developing its own atomic clock in the National Physical Laboratory in Delhi. So soon we will become independent. We don't have to depend on anymore on the outside, atomic clock, because it's very crucial for me. I cannot depend on a clock which is inaccurate, but I don't have today. I have to depend on outside. But very soon we will be able to meet our own requirements. Now, these are the two different segments: space segment, control segment, and the user segment. User segment is you and I. Very simple. It will have a very simple receiver with an antenna and an amplifier, because you are receiving signal from 20,000 kilometers or even more. Please note that ISRO's NavIC satellites are not on MEO orbit. They are on geo orbits, 36,000 kilometers. A signal received that are sent by the NavIC satellites are very, very weak. So we must have, and even GPS satellite 20,200 kilometers. So we must have a pre-amplifier with very low noise. And of course, you have got further processing elements and further, it is not a very, very complex unit. However, the importance is in the size of the chip. The chip that represents chipsets of GPS or NavIC in future are yet to, our own chipsets are yet to come. As I said, very soon we hope we'll get it. Next one. So there are a lot of things to be talked about signal processing. Though I get a hardware from a different country, I can put my own code, so I'm safe. So I'm still secure. I have got my own code. I can program. Indian software knowledge is very good. And certainly, though I get a chip from Taiwan or Qualcomm, I'm still safe. I can get my own code. That's the important part of the whole game. And still, we can do that. The main things are done in the signal processing section. Next one. This shows a very simple picture. Who are all the users? There are users who are trekkers, traffic management, boats, aircraft, even laptops can have this kind of a device. Survey and mapping, as I said. Jain University has, Jain University has many plans. We are doing total electron content, that is space weather. And we also have people working with the mobile platform. I'll tell you, show all those pictures. So it will tell you latitude, its position. When I am going around with my GPS or IRNSS or NavIC system, I know every 1 second I know the position. If I record all this position, I can come back and make a quick map by using a proper software available commercially. So this is another way, and also it's one of the latest demands or apps being done is for women's safety. Suppose there's a problem. Problem is in the sense you are having a threat. You can have a watch where you can press a button. That button will tell you to the nearest police station where you are. That means the threat. Like you have in many places, even in GPS, there's a danger is there. You press a button in your watch, it will alert the security people, and that is what we are. This is women's safety, and even doctors. doctors will use in where suppose you have a patient, not only the position of the, suppose a patient is traveling and he will press a button, it will tell you about his vitals and it also tells you about his position. These are some of the applications that are coming through in our in using NavIC. Please go to the next one. Fleet management. I was telling you, UPS, United Parcel Service, with lot of commodities, a very important device, equipment that is being, that is how it started. Application, it's called, it basically comes under fleet management. You can also control the train movement. There is also another application in remote sensing called mineral resource exploration, because each one of the satellites, each one of the GPS transmitters each one of the GPS has got a transmitter, and that transmitter can be used like a source of, I hope, okay. I hope I'll continue, okay?
Yes, sir. Yes, sir. Please, sir.
Okay, then intelligent vehicle system. It will be more than, it will tell you where you are going for traffic management and ambulance, police, all very effective in today. We are going very, all applications are dependent on GPS. Next one. So apart from that, next one, we have very powerful demand in aviation. As I said, recently we had a problem, recently a few days back. One of the possibilities is spoofing. We cannot rule out spoofing, that is introducing additional extra time so that you'll be confused. It's very dangerous. So there are some software adjusted in all A320s. They are adjusted recently after grounding hundreds of aeroplanes. It is today's news, what is happening in the world. Many aeroplanes are vulnerable to this kind of, if you are dependent on the GPS. It can be because other version is that there is an intense solar flare. So irrespective of your nation, who are the owners and all that, everybody will be affected. Whoever is having GPS or that kind of a NavIC or Galileo or Glona, they are all affected. However, GPS is playing a very important role in aviation. It's space transportation, as I told you. The rockets carry a GPS looking at the movement of the ejected satellite or its own position. Not only ejected satellite, but it is also having its own movement. Is nowadays newly done. NavIC has been mounted on the ISRO's launch vehicles, and that is one application. And maritime, of course, when you are going on the sea, there is no way. Apart in the daytime, you have to depend on some devices like this. Next one. So accuracies up to, as I said, positioning accuracy is relative positions up to 50 to 2 meters are available easily. For defense, it can be a few centimeters or millimeters. Again, we don't get access to higher accuracy. That is P code. Next one. So I was telling you about the importance of clock throughout the world. They are called international GNSS services. The 3 continuously operating ground station spread over 80 countries. If you are interested more, there is a link I have given you. And we have in India 2 IGS stations, one in Hyderabad and another one is in Bangalore, CMAX, near HAL, old HAL. So CM Max is under, it is in Bangalore, and CSIR or NGR, National Geophysical Research Institute in Hyderabad. They are the people who are having these IGS stations. So we are also part of the network. We are bound to give more information, share information with others. Next one. Key functions are, they have very good, very powerful, in simple terms, they have got chain of 40 hydrogen masers, 25 cesium. It's more like a redundancy. Number of, very, very powerful atomic clocks are available. They are available for all of us. They will available for as reference for the satellite and for the aeroplane, for the ground stations. Send it to the satellite, and the satellites, they correct their clock and broadcast to the users like us. Next one. So another, just a list of international organizations. There are so many stations, as for over 400 global observation stations. They give the knowledge of space. Geodesy is one of the very early science where we are position is important. Position information is very well given. They have the powerful laser ranging system, and it's very common, available throughout the world. And as I said, about 300 to 400 ground stations are available in the world, and they are serving all the people who are using GPS. Next one. So a general list of GPS, GLONASS, Galileo, Gagan, IRNSS. They're all designed for different orbits. As I said, altitude GPS is 20,000, Russians 19,000, Galileo is 24,000. ISRO, India, we are in geo orbit. We are in the geo orbit, we are regional. We are having coverage up to 1,500 kilometers around the country, but we are not global. Then we have almost 20 meters accuracy, so that we can dip. This is, as I said earlier, this is basically meant for AAI, aeronautical observations, for taking off and landing of the aeroplanes. The demand was up to 5 meters. We've been able to do that, less than 5 meters. Apart from that, there are some geo satellites, not only the IRNS satellites, geo satellite, there are what is known as Gagan. Gagan is GPS assisted, geo augmented navigation system. I'll come to that at the end. Sorry. So we are having a comparative thing. We have to go a long way, but today we have to replace. Some of the satellites are failing. One of the priorities of the country is to replace these failing satellites. As I said, one of the failing component, the GPS, it is a clock. So we are trying to catch up. So this is the status of the world. Next one. List of, again, whatever I have said. Other missions are GLONASS. Russian is already globally operational. Galileo partly operational. Baidu Japanese, Baidu is Chinese. Chinese are having very versatile system now. I'm seeing that Chinese are having both low Earth orbit, medium Earth orbit, and geo orbit satellite, so that they are very versatile, very powerful. They will become almost leading people on the global navigation satellite system. Compass. See, Baidu is only for the local. Compass is for the Chinese global. They are not yet operational. They are yet to be. Whatever I put here, supposed to be 2020, but not yet. So there is a large number of constellation of satellites in the space, and we have our own IRNSS is regional, Japanese QZSS, regional navigation satellite system for Japan to cover their own country, Asia and Oceania. Next one. Indian satellite, a few things about, I told you, ISRO and AAI, Airports Authority of India, they have been insisting. We started for them with a support for the navigation of aeroplanes during launch and during landing and takeoff. We have 7 satellites, and we have been able to cover entire Indian subcontinent and 1,500 kilometers around the landmass. Next one. IRNS refer to today. I told you. Hello.
Yes, sir, please, sir. Sorry, sir. Some interruption.
Okay. Now we have, as I said, ISRO Satellite Center is the lead center for developing the IRNS satellites. We have Space Application Center to develop the payloads, and ISTRAC Bangalore, MCF Hassan, and VSSC are the rocket components. They do the even MCF Hassan as well as Ahmedabad ISTRAC. They are the tracking station for IRNSS. This is a general view of the IRNSS. Next one. The next picture shows the constellation, 7 satellites positioned at various latitudes given in the picture. But more important is the ground segment. Ground segment is the one which is going to give you clock signal to periodically improve the update the accuracy of the timing. This is the complete configuration of IRNSS. Next one. Again, space segment consists of 7 satellites. The repetition. Please go to the next one. IRNSS coverage very clearly 40 plus minus 40 degrees east. For 40 degrees, as I've given you, 40 degrees east to 140 degrees east, and latitudes plus minus 40 degrees, because we have to cover the entire landmass, and the accuracy assured is 20 meters, though we are able to get better. It's a pessimistic number. We are getting what we are operating in the is the worst case. So we are getting better than 8 meters. Next one. Okay, now all the satellites are available. Now there are some disappearing satellites. If you have time, any one of you visiting Jain campus can see the sky plot where the satellites are visible, how many satellites are working, how many satellites of GPS are working, and also there are geo satellites which are supporting under Gagan. So this is a very powerful facility given under collaboration with ISRO and Jain University. Our students are making use of this facility and trying to make use of all the applications of IRNSS, that is NavIC satellite. Next one. Again, this is this coverage. Range coverage is about the 1,500, even more than that. They're more than 1,500 kilometers, but 1,500 kilometers are shown. Next one. This is the simple general block schematic of a GNSS receiver. Your mobile, what you have in your mobile, simple RF front end, signal processor, and navigation processor. Next one, that long, conversion. So we have a very simple lab. We have got a better lab. This is called IRNS User Data Analysis Lab in Jain University. It's nothing but a small receiver and a laptop which provides the software to analyze, give the position of satellite. All this supplied by the, we have a Accord company supplied it for ISRO. Most of the universities have got the advantage of making and including many of the satellite, not only government organizations, universities have got the benefit. They are using it, and we are lucky to have 2 receivers. Next one. This is an antenna which is mounted at the rooftop, that gives one hemisphere of observation. At any time, you may get maximum 12 satellites, which you can see in a sky plot. If you look into the sky plot software available in the Jain University, our campus, that software is shown on the display. And this is the antenna, and this is the university. This is the receiver. You can see the beautifully what is known as the GPS TOWC. This is a receiver, and receiver shows a LCD detail, latitude, longitude, and altitude, and TOWC. What is TOWC? Time of week count. Right from the day it was launched, the receiver is continuously counting. 0 is reset at midnight of Sunday. If you are using this today's midnight, it will be every 1 second you get a sample. Time of week count. So in 1 hour, at 1 a.m. tomorrow morning, you will get 3,600 count. At 2 p.m., 2 a.m., you will get 7,200, like that. It goes on, and this is a very easy to remember when you got the latitude, longitude, and what time. That's called time of week count. Next one. And the right side of the picture shows you sky plot, and also it shows signal to noise ratio of each of the satellites. You can see the vertical coordinates telling you signal level. Jumping, if you come in active system, an active system shows up and down jumping of the vertical ordinates based on the ionospheric and tropospheric disturbances. Next one. So this is a very useful exercise for the students. Students are mounted on this university van. They go around and they are taken some data using the GPS receiver, IR receiver mounted on this. Next one. We have gone around, the students have gone around some areas far away from the Jain University called Arkavati River. It has beautifully plotted a map or the track of the movement of the vehicle. This is about 3 different frequencies. IRNS has got L1, L5 and S band. GPS has got L1. All the 3 different frequencies follow each other very well. So the 3 colors are plotted for different frequencies, a GPS location. So this is a test study using IRNS's user receiver around the Arkavati Dam. Next one. Apart from the, as I said, apart from GPS, there are supporting like Gagan, GPS assisted, geo augmented navigation system similar to that is Gagan for India. We have our own satellite, GSAT, some numbers, 12 or something, and they keep on changing. They are working. They are supporting by sending a beacon, and you can also detect that supporting the GPS accuracies of 8 meters will become improved, or if there are some missing data, augmented by these. So each one of the countries will have their own ground-based satellite navigation system like Gagan. Next one. Gagan operation system, satellite-based navigation system used, as I said, it's called SBAS, satellite-based augmentation system, supported by, next slide tells you what are all the components. Next one. It has got 3 geo satellites, 3 uplink stations, 2 control centers apart from your 7 satellites. All of them are working together to support the accuracy. If you look at the way, how complex is your total mission, where space segment, ground segment is supporting the user segment. This shows that we have many reference stations. We have 3 geosatellites and uplink stations in Lucknow, in our Pina, as well as Pina, the Bailalu, and other stations, where you have uplink of not only uplink, they are also sending. Uplink is for communicating with the satellite, and also receiving downlink for geo satellite position determination. Next one. Now comes the last part of my position, my lecture. Differential position. Differential position is very simple. You know, you have a, in general, you have a known, very well identified point on Earth, measured by the Survey of India, and compare it with your whatever you receive from your system, and you can generate the error. So potentially, measurement are necessary to be supported by a well-defined object. well-defined ground station. Next one, this is called differential position. So what are all the errors? As I've said, typical numbers are given. These are all the position errors. Position because the orbit errors, clock errors, satellite geometrical errors, and ionosphere, troposphere, receiver noise, all those things are errors. We can't solve all the problems, but suppose I have two adjacent 1 meter, 100 meters away, many of them are common. So if I subtract the common, it should generally give you a glimpse of how I can cancel the errors. Common errors are cancelled. That's another way of looking at it. But next one, please. Okay. So all the all the GPS satellites will have a ground station, a ground station receiver station where you have DIR. That means you have augmented the differential IRNS is using ground station as an additional thing. I'll show you a picture of next one. So, are you able to go to next? Please go to next one. Okay. All these receivers, they are looking at the errors created by various satellites. They average out and find out the net error, and that error will be that's not from one satellite. All the satellites have their own contribution. And next one, to simplify the argument, I want you to note that more number of slides you will see from our Dr. Ramesh Raju on Friday, but I'll give a glimpse of what the differential, what he has done, what we have been doing in Jain University. Next one. We have got what is known as ground control points. They are all very, very well surveyed points on the ground. For many years, they have averaged and correct a meter or centimeter data is available. But you have to pay for it. Ground control points are very well defined and very confidential thing, and you have to coordinate with the Survey of India to get the ground control point. Next one. We have taken a few of them, one place, a few about 40 to 50 kilometers away from the Jain campus, and we have made use of the next one. For example, field experiments we have conducted in different 4 or 5 experiments we have done, and this one shows that for the first slide tells you about the reference station NavIC lab. You can see the display on the computer monitor. We can see the first section, top section, gives you this availability of 12 satellites, and the lower one tell you 7 satellites, IRNSS satellites. That tells you they are all working at that time. And you have mobile tracks are there. When you go to a different location, like for example, here, please go to next one, experiment number 1. Okay, mobile station is located at a place 72 hours, where we have averaged it out to determine what is the accuracy available from my station, and then determine the base value. And next one, different location. One we have mounted in the field itself, one in the lab. All these have been averaged because first I had to have my own errors. The errors are determined by these stations. Next one, I go finally to a very well defined place. Very well defined place where these ground control reference points are maintained in a public domain, public building. It can be a post office or it can be any of the civil applications. See, you can look at the way it has been mounted, marked. These are all the locations where we have the ground station, and we have to put our antenna, put a little bit away and by measuring the the IRNSS data, which is erroneous, comparing with the ground control point given by the Survey of India, I can determine the error. So this has been done in various places, and I don't want to go to the, as I said, we have number of data available to be explained by Dr. Ramesh Raju on Friday. I'll just give a glimpse of that, and all these have been done, and we have got very good results up to 5 meters, 3 to 5 meters accuracy. He will explain to you more. Next one. Okay, where are we? Nothing but lot of experiments have been done, and you go to the experiment 6, where we have plotted the data. Look at the way we have plotted errors in red, and after correction we get very good results up to several meters. It's not, even then it's not very good. However, it's better than meters to close to 1 meter, 1 to 2 meters. This is the way we have collected the data. Next one. And one more experiment we had. Please go to the last one. Data link experiment. That is, we have not only conducted the mobile platform on a mobile platform, we have worked on a system. Suppose I am working on a disaster-prone area or a secured area. I must know the position determined from the aeroplane, and I have to communicate to ground station using a link. So we have designed a communication link where suppose there is a disaster, and that has been identified by the GPS, IRNSS, but that should be communicated to the ground, and that link has been developed. We are not measured all the details. We are not taken to disaster area, but we are able to determine this experiment, link experiment we have conducted. We have been able to go to a complete a few kilometers, 5 to 10 kilometers. This experiment has been successfully done, and this is my last slide, where I have shown that the data is I have shown the red. You cannot read it. You will see more explanation by Dr. Ramesh Raju. That is, what is the important? Not only determining the position, I should communicate to the decision maker. It can be a disaster situation where the local community or local officer will take, for example, decision to move away from that. Unless I know what is the situation through the data link, there is no use of doing it. So that experiment has also been done by our this team, and this is the last slide of my presentation. And thank you for your patience. I hope you could get a glimpse of the total GNSS mission and also differential method. Very simple. Differential is you take a reference point, very well documented by the Survey of India, take your equipment there, make the measurement, determine the error, and apply corrections towards the unknown area. Thank you very much. Are there any specific questions for me? I would like to answer. I think I have maintained 1 hour, 15 minutes or 1.5 hours. Mukesh?
1.5 hours, sir. 1.5 hours, sir.
Thank you. Thank you.
Thank you, sir.
So, if there are any questions, I would like to answer, or you can send questions through my email. I will be happy to answer your questions. The participants might have a lot of questions. I welcome the questions. You can ask a few questions now, or you can send me a questionnaire through email. Agreed, Mr. Dr. Mukesh?
Yes, sir. Yes, sir. Any questions?
And I encourage all of you, all the faculty, to make a point to visit Jain University, look at the equipment. I hope some of you might be having the equipment. Our Mukesh sir had in his earlier college in Bangalore, in ACS college, he himself had an equipment. And a lot of learning things are possible through this equipment. And in future also, there will be opportunities for you to look for openings. ISRO will encourage academic institutions, like they have already done to many of you, many of the nearly 60, including some government agencies. But I wish you also understand how the equipment looks. Though you have seen in the display in my PPT, I encourage you to visit our campus and take advantage of some of the equipment and what experiments are being done. Thank you all.
Thank you, sir. Any questions from the participants, please? Okay. Now,
I think it's quite late. I think they may be feeling late.
Maybe, sir.
8:40. So I don't mind looking for your question through email. You can give me my email ID.
I will share the email ID. Yes, sir. Yes, sir. Thank you, sir.
Thank you. How many people participated, sir?
Nearly 120, sir.
Oh, very good. Thank you for all the, Shiva Kannu to everyone. Thank you. Okay. I'm happy that there's a good, audience, and I'm sure you'll have a lot of questions. As I said, send your questions through email. I'll be happy to answer. And again, welcome to Jain University. Participate in some of the experiments being done and take advantage of the ISRO developed NavIC. Thank you.
Thank you, sir. Now it's the time to propose the vote of thanks. It's my honor to propose the vote of thanks as we conclude today's session. Our deepest gratitude goes to our distinguished resource person, Dr. G. Raju, sir, for sharing his remarkable journey and expertise. Sir, your explanations on GNSS fundamentals, NavIC architecture, and the significance of differential NavIC have greatly enriched our understanding. I extend sincere thanks to our management, Principal Sir, HOD Madam, faculty members, and the AICT for their support. A warm thank you to all participants for making this FTP meaningful with your active engagement. Thank you all and have a wonderful day. So we will conclude the session, today's session, sir. Thank you, sir.
Thank you, sir. I'm getting some responses thanking me. I'm happy. Some of you have responded. Meenakshi, and other many more things. I'm seeing them. Thank you all. Good night.
Dear participants, please fill both the feedback session 3 and session 4 feedback forms.
Sandeep Mahendran, Kirutiga, to everyone, dear part kindly. Okay. Okay.
Thank you, sir.
Thank you very much. All the best. So shall we?